The next of our tricks for differentiation was called logarithmic differentiation, and that's when you basically leverage the properties of logarithms to make derivatives easier or even just possible. So in order to do this, you're going to need to remember the three properties of logarithms. The first property is the multiplication or addition property. The way that one works is it says, if you have the natural log of two things multiplied together, x times y, you can write it as the natural log of the first one plus the natural log of the second one. Right? The quotient or the subtraction property is a very similar deal. If you have the natural log of something divided by something, we can do it as the natural log of the top minus the natural log of the bottom. Note, I'm doing all this with natural log. I could do it just as easily with a common logarithm or log base 7, but as you hopefully remember from last year, the natural logarithm is really the best thing to use. The final thing is the power property. The power property says that if you have the natural log of x raised to some power, you can take that power and multiply it to the front instead. Keep in mind, all these properties work both directions, right? If you have two logs added together, you can also combine them into a single log. If you have two logs subtracted, you can divide the arguments and put it as a single log. If you have a number in front of a natural log or any logarithm, you can move that up as a power. Lots of times we go this direction simplifying to do the derivative, and then we go back this way at the end to simplify our answer and give us one nice compact answer. So we're going to use these properties in the following problems to take some derivatives. So my first question here, find y prime without using the quotient rule. You could do this using the quotient rule. You could do this problem as, the derivative of the natural log of something is 1 over that mess, chain rule, times the derivative of what was inside, which is going to give me some huge mess over here, right? What's easier is to recognize, hey, there's a natural log here. I'm not taking the derivative yet, I'm just simplifying. I could say this is the natural log of sine x minus the natural log of x cubed. And even then, we could say that x cubed is really just going to be 3 times the natural log of x. So now that we greatly simplified this problem, we just take this derivative. The derivative of this thing is 1 over the sine of x times the chain rule says times cosine x minus 3 times the derivative of natural log of x, which is 1 over x. I end up with cotangent x minus 3 over x. And I hope that you are astonished by how ridiculously simple that process was compared to the original option of going, oh yeah, we could just do a combo chain rule quotient rule. You could, but it's a disaster. Using logarithmic differentiation, using the process of splitting up a logarithm makes this so much nicer. So make sure that you're looking out for that when you have logarithms in a problem. Now, sometimes a problem won't have logarithms in it, but if we want to, we can sort of combine logarithmic differentiation with implicit differentiation to do some fancy stuff. We might look at this and go, man, this is going to be a terrible quotient rule. If only there was a natural log. If there was a natural log there, we could do so many better things, right? Put a natural log there. Take the natural log of both sides. The natural log of y is equal to the natural log of 2x minus 1 cubed over 3x plus 5 to the 4th. So now I'd recommend you pause the video here and think about how could you split up that natural log? How could you break this thing down to make the derivative much easier to work through? Hopefully you got that you'll have natural log y equals 3 ln of 2x minus 1 minus 4 ln of 3x plus 5. I skipped a step in there, but the idea is we're subtracting the top minus the bottom, and then I just brought the powers down, and that's where those came from. Now that I've got this thing in a nicer position, I can take this derivative. But because it's not just y equals, I have to do logarithmic differentiation. I'm sorry, not logarithmic, implicit differentiation. I'm going to get 1 over y times dy dx. Right? Then here, I'll have 3 times 1 over 2x minus 1, chain rule times 2, minus 4 times 1 over 3x plus 5, chain rule times 3. Right? So now I have 1 over y dy dx equals 6 over 2x minus 1 minus 12 over 3x plus 5. Next up, and I was hoping I could sort of fit this on the screen here, but I don't think I'll be able to. Next, I'm going to multiply this y over to the other side. I'll get dy dx equals y times these things. 6 over 2x minus 1 minus 12 over 3x plus 5. So then the last thing we can do is we can say, hey, I know what y is. We were told in the beginning of the problem that y was this thing. So I can take that and write it in the position of the y down below. Hopefully I'll remember this correctly. So this is going to be dy dx equals 2x minus 1 cubed over 3x plus 5 to the 4th, and then times this stuff inside. We could get a common denominator here. Depending on the needs of the problem, you may decide to, you may decide not to. For now, I want to keep this video on the shorter side, or at least not on the crazy long side, so I'm going to stop there. Again, not a super nice answer, but I think it's good to know that we have the option of doing logarithmic differentiation when we're presented with a problem that's a little bit complicated. Now, the previous problem was one where we were doing logarithmic differentiation because it was convenient, because it made it nicer. There are some problems where you have to use logarithmic differentiation, and this is one of those examples. To be honest, anytime you ever have a variable expression raised to a variable expression, like you have an x in both the power and in the base, you must use logarithmic differentiation. And the way it works is you say, okay, they want the derivative of this thing, so let's set it up. Let's say that y equals the cosine of x raised to the x power. They want me to find dy dx. That's what they want me to get. So to do that, I'm going to take the natural log of both sides. I'll get natural log y equals the natural log of cosine x raised to the x. But, of course, I can, take the x off the top and put it in front instead. And the reason that's so amazing is that, I didn't have any rule for taking the derivative of a variable to a variable power. But I do have something when it's something times something. I have the product rule, right? I can now take this derivative using the product rule and implicit differentiation. So if you haven't already done this on your own, pause the video, take this derivative and then check your answer. This derivative will be 1 over y dy dx equals, derivative of x is 1, so 1 times the natural log of cosine x plus x times the derivative of natural log cosine. That's going to be 1 over cosine x times the derivative of what was inside, so negative sine x. So at this point, I get dy dx equals y times natural log cosine x minus x tangent x. And the very last step is us recognizing that we know what y is. In the beginning of the problem, we declared that y was going to be cosine x raised to the x power, so in the end, my dy dx ends up being cosine x to the x power times the natural log of cosine x minus x tangent x. So this is a problem where we absolutely had to use logarithmic differentiation. We didn't have a choice. So anytime you encounter a problem that's like this, where you have a variable raised to another variable power, you're going to have to use logarithmic differentiation. If that example didn't make sense, go back and look at it again. I'm sure we have some practice with that in the assignment that you'll work through in class tomorrow. I'll see you then.